Brownian motion is the random movement of particles that are floating inside or on the surface of some medium. You've probably seen it before, but you might not realize it has a name. If you've ever watched black pepper move around on a bowl of soup, then that's Brownian motion. Now, would you believe me if I said that Brownian motion is direct evidence of the existence of atoms? A Roman philosopher poet named Lucretius first wrote about this in a poem titled On the Nature of Things in 60 BC. His basic argument went a little bit like this. Take a look at this animation. If matter was made up of atoms, then a dust particle floating in a sea of air would look a little bit like this. Notice that the big particle is being kicked around randomly due to random collisions. Now, look at what happens when I increase the number of particles but I decrease their size. The large particle isn't moving as much as before. In the first animation, there were less particles bumping into the big one. This meant that it was more common for the big one to get knocked in a random direction. In this animation, there are more smaller particles, which means that it's more likely for there to be a simultaneous collision on all sides of the particle. So, it rarely goes anywhere. Now, we can imagine taking the number of particles to infinity, but the size of the particles to an infinitesimal. Taking these limits is what continuous matter would look like, and this would mean that there can never be any random motion because there would be an infinite number of collisions on all sides and at all times. Therefore, because Brownian motion exists, matter must be discrete at a small enough scale, and thus we have atoms. So hopefully, this helped you understand Brownian motion and why so many physicists are interested in it. I'm going to show you how you can model it using a computer simulation. My goal is to show you the process of looking at a real physical phenomenon, trying to understand and model the situation, and the process of making sure that your model is as accurate as possible. Hopefully, by the end of this video, you'll get a better understanding of how to make and scrutinize your own predictions, which should help you become a better scientist. Remember, it's crucial for a scientist to be willing to be wrong. Suppose that we had a particle in the form of a pixel. The pixel can move up, down, left, or right. Now, let's place a fixed particle. The fixed particle will freeze any particles that move into it. I place the fixed particle in the center of this grid, and then I put 5,000 pixel points all around it. Let's see what shape it ends up making because of the Brownian motion. Here's the simulation, but sped up. Isn't that interesting? Instead of growing uniformly or growing in a smooth way, the Brownian motion created this complex and rough fractal. Let's take a break from Brownian motion to talk about something fundamental about physics. It's called symmetry. If you look deep enough, you can find symmetry in almost everything. For example, take a look at the equations we have for the Coulomb force equation and Newton's law of gravitation. The Coulomb force equation shows how charged particles interact with each other. The gravitational force equation shows that masses attract each other and explains how orbits work. These are 2 out of the 4 interactions that we have in the universe. Both of these display spherical symmetry or radial symmetry, and this means that the force looks the same no matter what angle that we look at the system from. One of the most powerful things about symmetry is that because it is so common and fundamental, we should expect to find some sort of symmetry in nearly every single situation. We can use this to see if our fractal is accurate for representing an actual experiment. Our fractal simulation should show something called radial symmetry. This is because the fractal is grown by random Brownian motion. We shouldn't expect the fractal to grow in any particular direction. Instead, we should see that any direction is equally probable. So how do we look for fractal symmetry? One way is to create a density graph. We generate a bunch of fractals and superimpose them onto each other. If we place enough, we should see a nice circle start to form because of symmetry. I imposed 50 of the graphs on top of each other, resulting in this very non-circular shape. What happened here? As it turns out, I made a mistake in programming the pixel motion. In real life, particles moving in Brownian motion should move randomly in any direction. My particles only like to move in 4. So, I went back to the beginning and I modified the code. I generated the full range of motion by instead using a random number generator to get a random angle. Then I plugged that number to sine and cosine inside of the program, and I got random x and y values for the direction of motion. And then I generated some fractals, and I repeated the process. I superimposed them onto each other, and bam! Look at this nice and radially symmetric fractal. Exactly what we needed. In practice, this would model something called diffusion limited aggregation. This has tons of applications. The one closest to our simulation is a process called electrodeposition. This is where charged ions stick to a charged rod that are floating in the center of some medium. This results in fractals just like simulations, but sometimes you can even make the fractal move three-dimensionally. Another interesting process is that of dielectric breakdown. The fractal shape that we generate with our simulation is related to the fractal shape that lightning and Tesla coils create. So, I hope you learned about Brownian motion because of my video. If you had to walk away and only learn one thing from all this, I hope it was the fact that I had to look at two separate equations, one that just displayed symmetry, just to notice that I had a problem with my simulations. I had a lot of fun making this video, and I hope you enjoyed it. Goodbye.